It's a great pleasure to welcome our speaker tonight, Dr. Brett Denevi from the Johns Hopkins University Applied Physics Laboratory. Her bachelor's degree is in geology from Northwestern University and her PhD is from the University of Hawaii, where she studied the composition and evolution of the lunar surface by using visible and near-infrared spectroscopy. She then was a postdoctoral researcher and faculty research associate at Arizona State University, and then joined the Applied Physics Laboratory at Johns Hopkins. Much of her work has concerned the mapping and geology of the rocky bodies in the solar system, the Moon, Mercury, and asteroids such as Vesta. She studies how the rocky crusts of these bodies developed and how they've been modified by volcanoes and impacts. She's also an expert in interpreting the data from the space-based optical remote sensing instruments, both imagers and spectrometers, that are used in missions to these bodies. And she's done a huge amount of work on the calibration of data from these instruments. She's worked on the calibration of the wide-angle camera on the Lunar Reconnaissance Orbiter camera, wide-angle camera, and she's worked on the calibration of MESSENGER's Mercury dual imaging system. She's co-investigator on the Lunar Reconnaissance Orbiter camera, our participating scientist on the Dawn mission to Vesta, the deputy instrumental scientist for MESSENGER's Mercury dual imaging sensor, and she leads the geology discipline group of MESSENGER's science team. Dr. Denevi.
Yeah, so
If at any point we need to turn off the last set of lights so that we can see the slides better, just let me know.
it looks pretty good, so I think hopefully we'll be okay. Yeah, so as was mentioned, I spend a lot of my time on the calibration, on planning, what are we going to image, in upcoming opportunities and things like that. But my science work focuses on looking at the volcanic history of Mercury and the geologic evolution of Mercury. And so it's a really fantastic time to be studying those things because we have never really had the data to do it before. Mercury is the last terrestrial body to have an orbiting spacecraft. MESSENGER has not been there all that long. We're going on 3 years. If you asked before, can we, Hubble has been used to look at different planetary bodies, but I actually work with a guy who proposed to point Hubble at Mercury, and the program manager said, over my dead body.
Oh, well.
Yes, too close. I think, that you could do it, but there's some risk there. You point a little off and the whole thing is fried.
Yeah.
But there was the Mariner 10 mission, which flew by Mercury 3 times in 1974 and 1975. And so this was what the map of Mercury looked like after that mission. Piecing together all the different images, you can see kind of a gore where images were missed there. But you'll notice that half of it is blank. So Mariner 10 saw about 45% of the planet. And if you think of how our state of knowledge of Mercury until very recently is really kind of like our state of knowledge of the moon before the space age. Seeing one side, we really knew nothing about its composition, speculations, but didn't know anything about it. Didn't know fundamental questions about, did it have volcanism? How did its crust form? And so that's where MESSENGER comes in. MESSENGER is a Discovery class mission, so it's a PI-led and proposed mission that's the planetary science's lowest cost category of mission, and was proposed quite a long time ago. I think it was over 11 years ago, 12 years ago maybe now. And so it's had a long life cycle. And part of that is because it takes a long time to get to Mercury. It's hard to get there because it is so close to the sun and in the sun's gravity well. And so it took over 6 years. There were 6 major propulsive events to adjust the orbit. And basically when the spacecraft launched, it had about 500 kilograms of spacecraft, but over half of the mass for it was fuel. And so now Messenger's been in orbit a while. We're getting down to the last little dregs of fuel left, and almost everything was spent on getting there and getting those major burns to get into orbit. And so I guess David, worked on designing some of that trajectory, and it was a pretty major accomplishment. And I have a slide here which should show some of that. It goes by really quickly, but what you're showing is launching from the Earth. You can see each flyby is marked. There was the first Earth flyby, a deep space maneuver, and then flying by Venus. You can see how the orbit adjusts after each flyby too, especially after that second Venus flyby. Another deep space maneuver, first Mercury flyby, a second Mercury flyby, and then third Mercury flyby, deep space maneuver. And it's chasing Mercury there until it's going to gradually catch up. And then there's the last big burn to go into orbit. And so, because it was a discovery mission, even still, with that low cost cap, that's why this complicated series of events to get into orbit. And I'll show at least a few images that are from those 3 Mercury flybys, which was essentially the whole Mariner 10 mission. But there was a lot of great science from that.
They had to recompute all that because the launch got delayed too.
The launch did get delayed, yeah.
It was supposed to be a little bit quicker.
There were 3 different sequences, which was a little bit longer than the other 2.
But it did allow a lot of time for calibration and things like that. Yeah. I work on the Lunar Reconnaissance Orbiter camera, and that's just like, what? You're there, operating immediately.
If we'd gone in a direct transfer, it would have taken about 6 times as much fuel.
Yeah.
So
Yeah.
it would have been 6 times less.
Yeah, and I should say, I'd love to hear questions, comments too throughout if you want.
This is where you could really use solar sail.
Yeah.
The gasoline has been going up, boy.
Well, I think they actually did use some solar.
They used the solar panels, the solar sail. It wasn't enough to do those big maneuvers, but it was enough to clean them up. So they, during the last they figured this out after, while it was out near Venus and the Earth, it wasn't so effective. But once it got close to Mercury, where it was closer to the sun, they were able to move the solar panels just by small amounts and then target the actual flybys precisely.
Yeah, and those flybys all came out within, 0.1% or something of their target. So they were hugely successful, and some of that was allowed to save fuel. And so Messenger was, proposed to be a 1-year mission, and now, we're going on with our mission. And that is because of those fuel savings that we're able to continue to operate there.
So the solar sail issue is one of braking and slowing it down?
No, I think it's more just slight
Adjustment.
adjustments of the
Small
trajectory, yeah.
Okay.
The
Placement as
they
opposed to braking or accelerating.
Yeah, I guess braking to go into orbit just came from,
Just-
a long series of burns
Okay.
that were very tense, but everyone was
bet
quite
so.
nervous. Yeah. And so here's a picture of the spacecraft being built at the Applied Physics Lab. And you can see the solar panels we were just talking about. You might notice something interesting about the solar panels.
Who manufactured this? Because this is pretty
The
good
Applied
hardware.
Physics Lab built this spacecraft. Johns Hopkins APL
Okay.
was built here.
That's pretty good hardware that works after 6 years. You can do all that precise
Yeah, and it's
maneuvering.
been in space for over 8 years now. Yeah, so the solar panels are over 2/3 mirrors because there's just too much sun. You gotta reflect a lot of it away. That's always a problem, opposite of the outer planets where you need more power, but here it's reflecting that light and heat away. And part of that also comes from the sunshade. So use the pointer here. This is a ceramic cloth sunshade that always faces the sun when in orbit. So it can never point more than 12 degrees away from the sun. And so, you know, successfully we've maintained that constraint and not, you know, burnt everything up in here. But you can imagine that puts a lot of interesting constraints on how you can image the planet, how your orbit change, you know, how you have to move the spacecraft as the orbit changes. And so luckily, well, not luckily, with great forethought, the cameras are on a gimbal so that we can adjust, whereas a lot of the other instruments are fixed pointing, so we can adjust to these kind of bizarre turns the spacecraft has to take. Another different thing compared to a lot of planetary missions is the orbit. So here's Mercury, here's the orbit, where the periapse is around, it's around 200 kilometers, usually it, you know, raises and lowers from the North Pole, but from the south it's 15,000 kilometers. And one of the big reasons for that is because the planet is very hot. It's radiating heat. You have the sunshade to protect you from the sun, but the planet is baking the spacecraft and all of the instruments. So you get really hot, and then you have a long time to cool down here. We started in a 12-hour orbit. Now in this extended mission, we're in an 8-hour orbit, so a little less cooling time, which had some effects, but you can still see that. It's also a slightly inclined orbit, so we're never passing directly over the North Pole, which has other implications that might come up when you...
Isn't the shaded side of Mercury quite cold?
Yeah, it is quite cold, yes. And we can definitely see that, you know, temperature profile changing as
Is there cooling on the opposite side of the spacecraft? Is some of that those big mirrors and stuff like that you also use to radiate? Can you radiate?
Yeah, there's different cooling mechanisms. I'm really not involved in.
Gotcha.
That's a kind of an engineering question, which is not my thing. But I mean, with the camera, it's a really interesting system of a wax buffer that keeps the camera cooler than most of the other instruments, where you know, the heat goes into melting the wax, and then that, as long as you have enough wax that the heat can continue going into melting that wax, it'll keep the camera cool. We've only fully molten, you know, had the wax totally molten where our camera started rising a couple times. So I love that system. It's so like Rube Goldberg machine kind of thing. But
Can we go back to your previous slide?
yeah, absolutely.
I'm not sure what you're trying to show here. Are you always keeping over the dawn dusk, or do you search?
Oh, it's just showing both. No, it changes. So the planet rotates under.
Mercury goes around the sun.
So it's not sun synchronous.
No.
It can't be. There is no, you know, gravity field isn't enough to get you into the sun synchronous.
But Mercury does have this weird 3-2 spin orbit resonance thing that means that we do end up observing a lot of areas on the planet under the same lighting conditions over and over. And I have a movie that kind of helps with that later. But so these are Messenger's instruments. There are a lot of them. I think there's 9 plus radio science. So this is actually a huge number of instruments for a Discovery mission. I also work on Dawn. The Dawn mission to Vesta has 3 instruments: camera, spectrometer, gamma ray neutron detector. That's it. So we have the 2 cameras. I always forget how this is laid out here. But okay, let's just start up here. Mercury laser altimeter for doing ranging, getting topography. These EPPS and FIPS are interested in the plasma environment surrounding Mercury. It's a very interesting space physics environment, so close to the sun. Energetic particle spectrometer, same kind of thing. Neutron spectrometer and the gamma ray spectrometer are looking at the composition of the surface, elemental abundances. There's a magnetometer at the end of the boom that's not shown. data processing, the X-ray spectrometer. I have a little bit about some of the data from the X-ray spectrometer, which has been really fantastic. Relies on solar flares to induce X-ray fluorescence, which can tell you about different elemental abundances on the surface. The MDIS, the Mercury Dual Imaging System, that has a NAC, a narrow angle camera for looking at high resolution, a wide angle camera, wider view, lower resolution, but also has 11 narrow bandpass filters to help look at the color of Mercury. Let's see. Oh, this is the solar monitor that goes with the X-ray spectrometer. MASCS is a spectrometer that both looks at the surface and looks at the tenuous exosphere, which sometimes gets called an atmosphere, but is basically just particles that get sputtered from Mercury, looking at the composition of those as well. And then here's the gamma ray that goes with the neutron spectrometer. So there's a huge abundance of data at this point. I mean, it's really going from no ever elemental measurements of the planet to this huge array of data now. But mostly I'm going to be focusing on the camera data. And so, as I mentioned, we did get a lot of really fantastic science from the Mercury flybys. And so I love this image because it was the first image that was downlinked during the first flyby. It wasn't the first one acquired, but it was actually kind of weird. There was some other spacecraft went into safe mode and had an emergency. So then when that happens, they get to steal all of your deep space network time. It was, I think, we're supposed to get images down, like 5 p.m. And then we didn't get any down until 2 a.m. And they said, okay, we were really excited. They said, okay, you can have one image, one image down, and then you can have the rest later. So, we looked through all the sequencing and picked out this image, which would show basically everything had not been seen before. It was that blank side of the planet, the globe where nothing was there. So that was pretty exciting because this was the Caloris Basin. Actually just this image alone started to tell us a lot of really fascinating geology questions. Like, you can see this basin, hopefully it's showing up, it has a little bit lighter plains inside of it. And so those are volcanic plains of a different composition than the surroundings. And just that right there had been an argument about the origin of those plains. Well, the fact that they're higher in albedo means that they have a different composition than their surrounding, means that they can't just be impact produced. They had to have erupted on the surface. So even one image was, a huge success there. So this is just a movie to show what happened. I think this is the first, or one of the first orbits, and after going into orbit. And so it's showing the spacecraft activities. There it is, snapping through different wide angle camera filters. These are little narrow angle camera footprints. This pink is the laser altimeter doing ranging once it gets closer to the planet. And this is showing images from the flyby in the background. And then even in our first few orbits, we are getting to terrain not seen by Messenger or Mariner 10 in some of the flybys. And the sequencing of all these different instruments together is really cool and takes a lot of planning. So this is a color image of Mercury, and you can see it looks kind of like what you expect the moon to look like if you took a picture of the moon in color. It's close to true color, although it's kind of debatable, how you make true color with these narrow angle filters. But it's pretty gray, maybe a little brown, a little reddish. And that's just to kind of preface what we do in enhanced color, where now that we have this global color mosaic at a resolution of a little better than 1 kilometer per pixel, but just showing well, there's a lot of things that show up here, but the enhanced colors from a principal component analysis, which really takes a fairly bland spectrum and pulls out the diversity in it and kind of helps you visualize it in a good way. You can see a lot of these volcanic plains, impact craters that have, you know, these bluer rays of ejecta emanating from them, fresh material exposed on the surface. There's the Caloris impact basin again. And so, while Mercury is, you know, fairly bland color-wise, there's actually still enough spectral diversity that we can really get a good look at composition, variety of geologic terrains from the color. So talking about a few craters, I've already mentioned the Caloris impact basin. This is one, well, we can leave the lights how they are, I guess, but this is about how it looked from Mariner 10. And, oh, that's a little better, yeah. So I added these arrows to show here that the Caloris impact basin, when Mariner 10 saw it, was right on the terminator, right, just barely showing on the eastern side. This is a, you know, a 1,500 kilometer impact basin, one of the biggest in the solar system. And, you know, there's this look at just the edge of it. So one of the things that I mentioned was that there was this big debate over whether these, I'll have another image here, but there's kind of these smoother plains within here. Whether, you can turn the lights back on, I guess, but whether those were volcanic or whether those were produced by impact ejecta. And the reason there was this huge debate about this was that Mariner 10 happened right about the same time as the Apollo 16 mission to the Cayley Plains. And those were targeting this region of the lunar surface that was thought to be volcanically produced. We'd go to these volcanic plains that flooded these low-lying areas, sample these really weird composition volcanic rocks. When they got there, they were all impact breccias, all fluidized impact ejecta thrown out from Imbrium Basin, one of the biggest basins on the moon. So because of that issue, and clarifying, you know, can it be volcanism or impact, that was a debate that basically continued until Messenger. And so this is a version of the enhanced color. Oh, it's coming out a little funky on here, but of the Caloris Basin. And you can see, as I mentioned, the composition of these plains, although we still haven't pinned down exactly what that composition is. It's probably a basalt-like composition, you know, like in Hawaii, like the lunar basalts on the moon, you know, all the terrestrial planets. Mars is essentially all basalt. But these kinds of analysis really quickly pin down that question of Mercury's volcanic history. And so, because, you know, Mariner 10 left this mystery of a basin just seen only on the terminator of the planet, Messenger did the same thing. This is actually from the second flyby. Do the lights again, me. This is a cool image. I hope it'll show up better. But, oh yeah, it's still not showing up that well. But there was this other huge basin, one of the other biggest basins on the planet, and probably the freshest, the youngest basin that could really give you a sense of, you know, the impact processes. It was also, you know, completely or half in shadow here. So if you want to see a beautiful picture, you can come look at my computer screen later. Another thing that we look at a lot with impact craters, oh, it does look better with the lights off, yeah, is looking at what they dig up. So we want to know the composition of the interior, the composition of the subsurface. And, you know, luckily, you know, we can't bring a drill rig with us, but these impact craters do that all the time. And we can have pretty straightforward relationships about the size of the crater, how far down did that crater dig, and most of the deepest stuff ends up right near the rim and sometimes in a central peak of an impact crater. So you can see this is a crater within the Caloris impact basin. Volcanic plains are this kind of tan color, and it's dug up this low reflectance material that we actually see exposed in all kinds of craters. And this is actually one of the more unsolved problems still is, what is this stuff made of? Why is it so low in reflectance? One answer might be, some interesting sulfide minerals, but we're still working on that.
What type of mineral did you say?
Sulfides. So like troilite, FeS, but other weird ones, oldamite,
That's what you
geekiolite,
find in some of the meteorites?
and things.
The sulfides in the meteorites?
Yes, you do, yeah. They're very common in some meteorites, especially troilite.
Does the very high temperature environment affect the mineralogy?
Yeah, and it doesn't so much affect what may have erupted or formed on the surface, but it does affect how certain minerals are preserved on the surface. And actually, that's a great question that I'll have in a few slides. We can look at some of the interesting effects that might come from that. So this is Balanchine Crater, another crater that is excavating this dark material from the surface in an asymmetric way. So it's just part of its ejecta is this low reflectance kind of blue in this 1,750, 430 nanometer combined color image. And one of the great things about working on a messenger is that you get to name the craters. And, well, they have to be approved by the International Astronomical Union. But Mercury craters are named for artists. And so I've been dancing my whole life. There were no dancers or choreographers on Mercury. So I got to name this crater Balanchine for George Balanchine, founder of the New York City Ballet. And I picked this one because this kind of swath of blue material reminded me of the blue tutus in one of his most famous ballets called Serenade. So yeah, if you actually, anyone can propose a name for a crater too if you want. They just have to be famous 50 years ago, dead for 3 years at least, and an artist, can't be on another planet. One of the things that we like to look for a lot is fresh craters, because not just the high temperatures on Mercury, but being so close to the sun, the solar wind is really intense, and the surface, it has a magnetic field to protect it somewhat, but it doesn't do a great job. And so as soon as something is exposed on the surface, it starts to be affected by this space weathering process. And if you're looking at, reflectance spectra, looking at the way light's reflected to try and understand what minerals are exposed by this impact crater, that space weathering process kind of just masks what signal of the minerals is there and kind of hides it. So unfortunately, even some of these fresh craters have already been so affected by some of this space weathering that we still have a hard time with understanding what the composition of the mineralogy is here. And then just an example of one of the most spectacular rayed craters on Mercury. This is Hokusai up here. It's only just under 100 kilometers in diameter, but you can see how even just this one crater has affected the surface, throwing out these rays of material, across pretty much the whole planet. You can imagine a crater like the Caloris Basin, 1,500 kilometers, what that did to the planet.
Are you surprised at the distribution of craters across this planet?
Yeah, and actually,
because it seems to me that most of it would be around the equator, equatorial plane, whatever that is, because I don't know how it tilts. But
I think it's usually pretty uniformly distributed.
It is. That's what I was looking at, and that's what really surprised me as I started looking at more and more pictures of this planet, because I thought that that what was being attracted by the solar gravity would affect the equatorial plane.
I mean, very slight differences, but overall, I mean, the whole surface of all planets is just totally beaten up by craters.
That's amazing.
And where you have fewer craters, Actually, first of all, Mercury does have an interesting story with its craters in that it is not as cratered as the moon, which is interesting because Mercury, actually, you'd expect more craters. And that is a consequence, we think, of volcanism, some kind of early resurfacing that, wiped out the earliest forming population of craters. And so as, it wiped out that first population and then has been cratered since. And then in huge regions, around 30% of the planet actually has these smooth plains. And this is maybe not coming out the best image here, but hopefully you can see, this area over here, very cratered. And then these areas right in here, less cratered, so younger. Although the differences are still something like a difference of, instead of being around, 4.123 billion years old, it's 3.9 or 3.8. So not as much of a difference as you might expect. But yeah.
Do we think that Mercury has a molten center similar to the Earth, or has it completely cooled off?
I think, yeah, they still think there is a molten core.
Okay.
I think, gosh, I'm pretty ignorant in some of my the geophysics of Mercury sometimes, but it does have. It has a very weak one compared to the Earth, but it does, and it does have a molten core. And one of the bizarre things is the structure of that core and how it relates to the geophysical measurements being taken lately, because the geophysical measurements are very hard to match. They've come up with all these bizarre scenarios like a dense inner core, a liquid outer core, and then a very dense anti-core, they called it. So, I mean, it's very hard to match how the structure and get that all to work out well. But was there another question?
Yeah, you'd mentioned that the last bombardment was about 3.8, 3.9 billion years. That's part of the last heavy bombardment.
Yeah, that may have been something, perturbed by resonances with Jupiter and, yeah, throwing everything into the inner solar system. Right. And Mercury definitely matches what the cratering record is on the other planets for that kind of heavy bombardment, late heavy bombardment at around 3.9 or so billion years ago. Yeah. So here's another example of I think this is actually the same scene, different view and in color, showing these volcanic plains which just went in, breached the rim of, this is Faulkner Crater. My husband's a writer, so I get to name craters for him too. But breached the rim of this crater, 168 kilometers in diameter, still pretty big here, flooded this crater and filled it in. And some of these, embayment and filling relationships of these craters, these plains are hugely expansive. One of the plains is nearly as big as 2/3 of the continental U.S. So compared to some of the biggest flood basalts known on Earth, these are even more massive. And they're thought to be just kind of this massive flooding of basaltic material, where it's kind of been compared to like filling a bathtub, basically. The just really low viscosity fluids filling up and flooding these huge expanses of terrain. And this is actually in one of those big flood basalt plateaus where you can see not only craters that have formed on top, but craters that have been buried and are just barely showing from beneath this lava. So lava flooded over this crater. It had a little, sinking here as it cooled in the interior, and you can just barely see the rim. So that's one of the ways we look at how deep these volcanic plains, how much the volume of the fill was, by looking at these craters that have been filled up and buried by this volcanism.
Does that one at the top right have the double central peak?
It looks like it has got like a little cluster of peaks. sometimes instead of just one nice peak, it gets a little central peak cluster. Yeah?
Does the extent of the flooding suggest that there's a thin crust, during the late heavy bombardment?
That's a really interesting question. Why do some areas have these huge expanses and others not? And that's one of the things that I study, so I like this question, is how does where volcanism occurred, how does that relate to things like crustal thickness or, heating from radioactive elements? And there is some correlation with where you have a thinner crust. It's easier for magmas to erupt to the surface. But it's not a one-to-one thing. You have plenty of areas of thin crust where we don't see any young volcanic regions. So it's also affected by the tectonics. Mercury has a lot of contractional tectonics, and that makes it harder for erupting magmas to get to the surface. But yeah, and some of that is actually hindered by MESSENGER's orbit, in that we get a lot of really great measurements for the northern hemisphere and not so much for the south because we're so far away. So things like models of crustal thickness, we can do it in the north, but not in the south so well. It makes it harder to answer with half your data missing. One of the really big surprises, this isn't coming out so well on the screen, but I think you can still get the general idea from this, is these really bright features. Actually, this area was so bright, it was seen from Earth-based telescopic absorptions. People assumed it was a really bright impact crater. Someone wanted to name it, the guy who found it wanted to name it Copeland, but it didn't turn out to be a crater, so it couldn't be named that. It's actually an pyroclastic eruption. So instead of this nice effusive volcanism, this deposit had a lot of volatiles, a lot of gases in the magma. So when it got close to the surface, it exploded and rained down little glass beads that left this kind of bright halo around what is like a little central depression there. And then down here you can see another little similar kind of episode that's occurring in this basin, Rachmaninoff. And this basin is as young as around 1 billion years old. Still old, but young for Mercury. And it's thought that this pyroclastic eruption and there's a volcanic fill in here are, they're obviously younger than the basin. So that's really fantastic that Mercury continued, well into its history to have the amount of heat to be able to produce these volcanic eruptions. And one of the surprising things was that it had enough volatile elements to have these explosive eruptions. Because Mercury is so hot, and some of the scenarios that were imagined in its formation, I think pretty much all of them actually ruled out a lot of volatiles in Mercury's interior. And so seeing, and this isn't the only one, all kinds of these pyroclastic eruptions around showed that actually something's a little off in the models, because all of these volatiles were able to survive in fairly large abundance, more so than the moon for sure. Zooming in, this is actually part of this, you can't see so well here, but zooming in on the vent here, this is an example of one of our targeted observations with the narrow angle camera, and the kind of image resolution you can get down to around 10 meters per pixel. But this is part of that vent where it's collapsed down here. You might notice, even on the screen, it looks really good how smooth the surface looks. It looks kind of, in a lot of the images, it looks kind of velvety and soft, and that's because of this little blanket of these fine pyroclastic glasses and beads that's just coating the whole area. Still on the topic of volcanism, I just wanted to touch on this because it was one of the things I was the most, and many people were the most interested in, were the first elemental abundance measurements of Mercury's surface. And so just from looking at aluminum, magnesium, calcium, one of the leading ideas for what Mercury's crust was made out of was, well, it's kind of, boring spectral slope, and it's kind of bright. It looks like the lunar highlands. So it's probably made out of the same stuff as the lunar highlands and orthosite. And this, one measurement or a series of measurements here completely disprove that. You can see, like, here's the highlands of the moon, high in aluminum, high in calcium from this plagioclase rich rocks. And then Mercury is plotting all down here. And same with, in terms of, magnesium and aluminum. Mercury is plotting actually in this field of rocks called komatiites. I don't know if any of you have ever heard of a komatiite.
That's a new one for me.
Yeah, so you've probably all heard of a basalt, right? A basalt, a komatiite is kind of like the more extreme basalt. It's when you get way more melting of the interior. You can get over 50% melting of the mantle. So it's a rock that forms when the interior is really hot, and they're only found very early on in Earth's history. So there might be a lot of these kinds of rocks on Mercury's surface, suggesting that early on there was a lot of melting and volcanism erupting onto the surface.
Mafic rock?
It is a mafic rock. They're usually also high in magnesium, and most mafic rocks are also high in iron, but Mercury has almost no iron in the crust. It has a lot in the interior. Yeah. So, as I mentioned, that just ties into the question about cratering and this population of missing craters. If you had this huge amount of melting and early melting in Mercury's history, that fits with this story of huge eruptions erasing a lot of Mercury's earliest surface. Talk a little bit about the topography.
Before we go on that, could you remind us, you had those colors, the blue and the yellow.
Yeah.
And I'm sure that wasn't that false color. What do these colors really represent?
In terms of, so they represent, as I mentioned, they're a principal component analysis. So what's being pulled out and displayed in red here is this. It's basically spectral slope. If you have a red spectral slope or a flatter, shallower spectral slope. And so that's telling you things about, like, these sulfides, they have shallower slopes usually. So they're gonna show up, as lower in this, and they are coming out blue. In the green band is basically just albedo, how bright is the surface. And then the blue is a ratio of two bands. So it's a separate way of basically looking at spectral slope. The first way is a little more involved, and it kind of seems to remove some of the effects of space weathering and maturity and things like that. But yeah.
And what is that? Does one of these colors tell us what is the newer material?
Yeah, although not in this scene. Some over here. So kind of the newest stuff comes out as kind of turquoise, high in reflectance, and it has a very a blue spectral slope, shallower, bluer spectral slope. But there's nothing that fresh in this scene, I guess.
Okay, thank you.
Yeah. Thank you for asking that.
As you're looking at these colors, you're looking at the intensity of the color, and
so
as much as the color, right?
So this is kind of just a visual representation to help you kind of break out what are the major terrain types, kind of classify things, and then when you want to really look at them more, you pull out the individual reflectance spectra or the elemental abundances and things like that. So the topography, here's some more great colors, but this is just color-coded in terms of high and low. And so, as I mentioned, with the volcanic plains in areas of low crustal thickness, these are some of the volcanic plains here filling in these lows up here in the northern hemisphere. And what this comes from mostly is the laser altimeter. And this is a view looking down from the north and then looking from the equator. And so this is one of those instruments that really suffers from Messenger's orbit, in that you get past the equator and it just can't see the planet anymore. It fires its laser and it doesn't get enough signal reflected back to it. So we have to do a lot of other things to kind of help us fill in the south. One of those is stereo imaging, looking, 2 different look directions and getting a stereo angle to get topography that way. One of my favorites is also limb imaging. We do a lot of limb imaging just so you can, in one little profile, you get the little topographic variations along the horizon. If you do,
really beautiful.
Isn't that beautiful? Yeah. So this is a 17-kilometer crater, but yeah, they have this kind of technical purpose. But the images come out really spectacularly a lot of the time, and I love these because they, most of the time we're looking straight down nadir, and these are all the kind of view out the airplane window kind of perspective. But yeah, when you put together all these different limb profiles that you get from these limb images, that helps fill in the southern hemisphere as well. And this is that same Rachmaninoff basin again, just showing exaggerated 7 times topography, but to help you get a perspective of here's the rim, here's this inner peak ring of mountains, and this is the volcanic flow that started in the middle here and kind of breached this peak ring, filling in some of the exterior as well. But having the topography really helps evaluate the geology as well.
What's the altitude of the highest part of those ring mountains?
Oh gosh, I would guess around, you mean the rim versus,
Yes.
or these mountains? It's a couple kilometers, is my guess, on the order of a few kilometers.
Since the gravity is less, it could clearly have more extreme features on the Earth, right?
Well, the interesting thing is that
It's so hot, and that would tend to flatten things.
well, what tends to flatten things, like for example, Venus is flat as a pancake, and that's all the volcanism filling things in. And some of that, Mercury, I think it's up to 10 kilometers of total relief, highest, lowest point. I think Mars is something like 30 kilometers.
Right, because it's cold and less gravity.
Yeah, and they have, more of these like shield volcanoes, which kind of build up topography and more viscous lavas and things. But yeah.
Has there been any postulation of because you're so close to the sun, thermally generated movement of large planes, and just because it's the heating and cooling.
Yeah, it's not hot enough.
They said they were postulating that was happening on the moon, that there was some movement of the surface that accompanied exposure to gravity of the Earth and stuff like that. And I would wonder if heating and cooling here would be that extreme.
It definitely has effects. I'm sure for a lot of the rocks, there's thermal cycling that leads to fracturing and things. Definitely. But in terms of things we can really observe, it's more of, because Mercury's in this 3 to 2 spin orbit resonance, it ends up with some parts of the planet facing the sun when Mercury's closest to the sun more often. So some parts do see more heating than other sides of the planet, even at the equator. So we are looking at, different effects from that as well. Okay, a little bit about tectonics. This was one of the first observations from Mariner 10, was that there are these huge tectonic faults. The image is around 400 kilometers across, big thrust faults that go across the planet. Here's another example with Delaware for scale, I guess, but showing just how you have these terrain of a huge, you can see really well in this kind of perspective view of this kind of crust folding and buckling across. And it was postulated from Mariner 10 that you had a global series, but they saw only half the planet. You had a global series of these faults, and the whole planet was basically covered with these tectonic features that are formed through compressive stresses. And so this is a weird projection, but a map of Mercury, excluding, Caloris, of all of the thrust faults on Mercury. And you can see they're all over the place. And there's thousands of these features. And if you add up how much contractional, how much strain was accommodated by these contractional features, you find that there's anywhere, it's still debated, between 1 kilometer is a very conservative estimate to 4 to 5 kilometers of radial contraction of the planet as it cooled. And so it's basically, thermally contracting. You have this somewhat brittle crust, and it's cracking and folding over itself. And it results in, these spectacular tectonic landforms, and it affects the history of volcanism and things as well.
I've heard also that because of the Caloris impact, that on the opposite side of the planet, there were
weird terrain.
Yeah,
that's what it's called, actually, weird terrain. It's just this jumbled up terrain, and one idea is that there's actual ejecta that kind of converged on the opposite side of the planet. Also, maybe shock waves that disrupted the surface in that area. So Caloris is the only area, the only basin where we really see that for. But the moon has those antipodal deposits or features as well.
Was Mercury actively volcanic early in its history, or is it still today?
Nope, it's done.
What?
Early, largely early, and tapering off. The youngest deposits might be as young as 1 billion years old, but nothing younger than that for volcanism.
I noticed that thrust fault you showed a couple slides back cut across some of the craters.
Yep.
Meaning it's more recent, right?
Yep, and that's a fantastic way to date some of these features. But although the thrust fault may have predated the crater and then continued to be active after the crater formed. But that's, they look for all these relationships with craters, little craters that are eaten by these scarps and things. I think I'll just quickly go through a couple more examples of some of the really bizarre tectonics. Although almost everywhere is compressive stresses, here's an example of extensional stresses, where you have these troughs that are forming within the center of Caloris Basin, radiating out from the center. Really weird looking. And hopefully you can see on this next image just how weird this radiating series of troughs extending from the middle of the basin. And then you get out here and it's all totally jumbled up. Wrinkle ridges, thrust faults, extensional, everything inside this basin. So if you ever look at a tectonic map of the Caloris Basin, it's really weird. One more main topic, I think I just wanted to get to some of the features that we see that we think are affected by the high temperatures. So this is the crater Cortez, and you can see in the bottom this really strange deposit that we call hollows. It looks kind of etched, and like in these low areas, you're basically having material that's being eaten away. Some features that are similar are Swiss cheese terrain that forms in Martian polar deposits. So basically areas where you have a volatile material that is eroding on the surface. And wow, it's really raining out there. Here's another image just showing where around these are peak mountains in the center of a crater, and around those peak mountains you have this floor that's kind of eroding away from them, and then this kind of bright halo deposit surrounding those. And they're really spectacular,
What would
beautiful
cause the
images.
erosion? What's the idea? I mean, there's not any water, right?
Right. That's the
Obviously.
exciting thing. What's causing it? So I think that is something we haven't pinned down, but I think the generally favored idea is that you have a mineral that, can form in volcanics or is exposed by impact craters. These features are often in impact craters. And it's stable inside Mercury's surface or below the surface. And once it's exposed on the surface to these hot temperatures, it just starts being eroded away.
Oh, so it's a metastable, but then with the low pressure, it sort of...
But the reason we think what is eroding it is the heat, but also the interactions with the solar wind, these charged
Oh, right.
particles that are, constantly bombarding. And materials like sulfides are not as stable or not as resistant to the solar wind, so they'll erode faster than the surface around it.
So all those protons and maybe even helium-3 and helium-4.
Everything coming off the sun, yeah, it's causing some damage here.
Well, since Mercury is so close to the sun, is it possible that the tidal forces of gravity from the sun is causing some of the deformation on the planet's surface?
Not in these small scale features here. These are all tiny little features, but definitely earlier in Mercury's history, that would have been a larger effect. Now that it's more cooled down, volcanism isn't happening. Yes?
Would hydrates give that eroded effect when exposed to the sun and
Maybe, but we have no evidence for those kinds of minerals and features on the surface. So when they erode too, one of the reasons we think the solar wind is involved is in kind of sputtering. You get these higher reflectance with a bluer spectral slope. That's the color in this picture means deposits around these little hollows. So you can see where they're forming on these little mountains on the floor here, and they, as the material I think is sputtered away, it leaves this little halo of debris around it. Okay, actually I think this is the last topic, ice. Mercury's hot, but there's ice on the surface, but only in very few places. And those places are all in permanently shadowed regions near the poles. Mercury has very little inclination in its orbit, so there are places, if you watch this movie, you can see some of them. This is one solar day, which is around 180 or so Earth days at Mercury. And as the sun goes around, you can start to pick out places, especially there's a big crater right at the pole here. You never see its floor. You might also notice, is there a glitch in the movie? Why did the sun stop moving there for a little bit? And it will happen right about here as well. That's part of this weird spin orbit resonance. And if you're standing on Mercury, you'd actually see the sun kind of go in the sky, stop, move backwards a little bit, keep going. Fascinating. So yeah, you can see areas here, that's staying facing the sun longer. So you do have these asymmetric
What's the
heating.
approximate area of that ice potential area? It could be a cold wrap or let's say helium-3.
The area, it's hundreds of kilometers.
So hundreds of kilometers.
Yeah, let's see if there's a scale here on the next one. Image width is 1,000 kilometers here. So yeah, if you...
A couple of 100 kilometers then.
If you're looking at the, this image, the colors mean percent illumination. So black, it's never illuminated. So there's a lot of these areas in the South Pole. And in the North, it's just easier for us to monitor the South because we can image from farther away a lot. That will have stable ice deposits. And the reason that it's actually way more ice than the moon. This is the North Pole, and colored in yellow are radar observations that suggested really radar reflective material that was thought to be ice. And Messenger's neutron spectrometer can directly measure hydrogen and finds plenty of hydrogen exactly where you would expect it, and only there.
Even more than on the moon?
Even more than on the...
Already wetter than, let's say, deserts?
I don't know. Maybe in the poles at the moon it might be wetter than a desert, but the moon is... There's been a lot about lunar water lately, but the moon is still pretty bone dry.
But
yeah.
I mean, the Clementine stuff.
But where it is different than the moon is that the moon is thought to have subsurface ice kind of mixed in the regolith in these mixed in with the soil in these permanently shadowed regions. Mercury is thought to have big deposits of relatively pure ice that might be right at the surface. And so what we're doing with the camera team now is really fun. This is Prokofiev, one of the permanently shadowed craters near the North Pole. So we take really long exposure images as long as we can, and it's kind of complicated because
There's a beautiful scale there too.
Blades, yeah. So this is one of the first images of some of this permanently shadowed area. Now I should say this is not all in permanent shadow. This area over here just happens to be what was in shadow when this image was taken. So this area over here is the permanent shadow, and then this in yellow is the radar observation showing where you get this really reflective deposits. And if you go back, what we're kind of excited about, although it's, you know.
Is that lit just by starlight then?
It is lit by reflected sunlight reflecting off of the walls of the craters,
okay.
yeah. So we think we may be seeing some actual differences in the reflectance on the surface. Now the laser altimeter can bring its own light. It shines a laser into the crater, it gets reflected light, you can get a measure of reflectance. They see some areas that are very bright. So we wanted to look with our camera, can we see these areas? And hopefully you can see that there looks like there's a seam here, or kind of a line here, where it's a little bit brighter over here than over here. And we think that that is real. It lines up almost perfectly with where you see this radar bright deposit. So you might be looking at ice right there on the surface, which is pretty cool and pretty impressive. So, Messenger is still ongoing. We have over 170,000 images right now. These are some of the interesting geologic things that I think are really cool. In terms of what's next, well, we're already past here. We're onto this chart now. So this is kind of a weird plot, but I think it's really cool because it's showing the date as you get out to 2015. And then our periapsis altitude, so our closest altitude we get to the planet. You can see, up here right now we're at 450 or so periapsis altitude. As we go down through here, you can see, wow, we're getting pretty low. And so these OCM are orbital correction maneuvers. So we don't want to get too low. Boost back up here. And then we have these 3 really low passes that are going to be phenomenal. We're able to get images that are, a few meters per pixel, and some of these other instruments that look at the composition and things will get fantastic measurements. So we'll get down here to around 20 kilometer altitude. Boost it back up, go back down, boost it back up, go back down. This will be it. That's all the fuel left. And they've been pretty good at estimating how much fuel is left, but they'll burn what they've got, and then you can see down here, altitude of 0 in March of 2015. And so this is assuming that NASA comes through with the funding to continue operating, which is not trivial right now in these budget climates. We actually proposed 2 scenarios for an extended mission. One where we would continue operations all the way to the end. One where if they don't want to continue the funding, all of this will still happen out here, but we won't be listening.
Oh, jeez.
Yeah,
But it
so
will end up
write your
in
Congress
2015.
people. Yeah.
No matter what, because.
It can't go any farther. There's no more fuel.
Because it will actually crash into the planet.
Yeah.
Yeah, if they don't do the OCM maneuvers, it'll go in August 2014.
Yep, and so we have, so we're still waiting for news on funding for the second extended mission, and that should We should have already had it, but it should be soon. And we're hoping for good news.
Will it do like the Ranger missions and take photos right until
Oh,
it
if
smashes in?
only
or-
we could do that. We can't get the data back. We'll be able to image up pretty close to the end, and those 20-kilometer passes will be fantastic. But in order to turn and point the antenna in the right direction and all that, we won't be able to get the data back. After Messenger, there should be Bepi Colombo, which is ESA and JAXA's mission, which involves 2 orbiters, one closer in looking at magnetic field, gravity mostly, one that has a suite of instruments that are complementary to Messengers. And that is now scheduled for launch in 2015, I think, and to get to Mercury 2023 or so.
Who's funding this?
ESA, Europeans, and the Japanese, I think, are largely responsible, JAXA, for the smaller magnetosphere orbiter.
Will they get
And you
close-
can turn the light, that's it mostly, so you can turn the lights.
Will they get close in over the half of the planet you're far away, or?
Actually, this is a great slide because you can see their orbit. We just had a joint science team meeting with them last month in Chicago, and their orbit is evolving because you can see actually they have a much closer in orbit. So that's a thermal problem that they're working on. But their orbit is going to have a periapse at the equator. So that'll help for sure. And they have different kinds of instruments. They have a thermal infrared spectrometer and things that'll really help for composition and things too. But